Hello everyone, this is a presentation for the Unit EE312 mini project. The title of the project is Temperature Process Controller. The group members for this project are Siddhant Kumar, me, the narrator, and Shivnesh Ram. Let us move on to the outline of this presentation. So, for this presentation, we will be looking at the following subtopics: objectives, introduction, temperature plant, transfer function, PID controller, lead lag compensator, step responses of the PID controller and the lead lag compensator, root locuses of the two systems, Bode plots of the two systems, and finally the conclusion. The objectives of this mini project were to design a PID controller and lead lag compensator for the temperature process control system and to compare the two PID and lead lag compensator systems. The overall system should be stable and have a 5% settling time that should be less than 12 minutes or 720 seconds. Introduction. Temperature control is useful in a wide range of areas, such as industrial, household, research, and many more. We will look at a temperature process system and determine its process characteristics and response. This is done by intentionally causing disturbance in the temperature process via a step change, recording its open-loop response. This method was created by the two scientists J. B. Ziegler and N. B. Nicholas. The transfer function obtained will then be used to calculate the PID controller and lead lag compensator equations. The following is a schematic of the temperature process plant. To the far left-hand side of the schematic is the DC source whose output is connected to a comparator with hysteresis. This comparator is also connected to a triangle wave generator. You may also notice the DC source output is connected to a DC voltmeter. The comparator is then connected to a solid-state relay which is connected to a power source. The signal from the solid-state relay is then transferred to the heater. Over here, the electrical signal is converted to heat energy. The energy then flows through the radiator to the temperature transmitter, and then finally we have the output of the process plant. After conducting the experiment, the parameters of the temperature process plant were found. The dead time was equal to 45 seconds, time constant was equal to 200 seconds, and K, the process gain, was equal to 0.8. Hence, the following transfer function was found. PID controller. For designing the PID controller, the following parameters were set. Overshoot was let equal to 3% and 98% settling time was let equal to 2 seconds. The following were the desired poles. Before calculating the PID controller, we have to first calculate the PI component of the PID controller, and the following equation was found for the PI controller. Furthermore, the PD controller equation was found to be the following. After calculating both the PI and PD components, the final PID controller equation was found. The K value for the PID controller was found to be 250. Now for the lead lag compensator part. Taking the same requirements as previously stated, overshoot and settling time, the following lag compensator equation was found. Z lag equals to 0.04, P lag is equal to 0.01, and K was equal to 660. Please note, Z lag is usually calculated by cancelling a pole with your original transfer function. But since our transfer function had only one pole, we chose z leg to a value that was near to the origin. After the leg compensator equation was found, we then moved on to the lead compensator, whose equation is as follows. Z lead is equal to 1, P lead is equal to 0.36, and K is equal to 900. After computing the lead and lag compensator equations, the following lead-lag compensator equation was derived. Here is a root locus plot for the original transfer function. As you can see, there is only one pole at -5 times 10 to the power -3. The following is a body plot for the original transfer function. As you can see, the magnitude part of the body plot shows very little change, and the phase part of the body plot has some change. The corner frequency of the magnitude part seems to be around 10 to the power -2. Now we move on to the plots for the PID controller. The following is a step response obtained via the PID controller. As you can see, the settling time was reached with 326 seconds and an overshoot of 3.33%, which was as desired. Here is a root locus plot of the system with the PID controller. As you can see from the original root locus plot, this root locus plot has two poles and two zeros, and it is symmetrical about the real x-axis. So we know this system is a stable system. Moving on to the body plot of the PID controller, it is seen that the magnitude changes over a wide range of omega. And here is the frequency change over a range of omega. It is seen that the corner frequency is around 10 to the power -1 for the body plot of the PID controller. Now we will look at the plots for the compensator. This here is a step response for the compensator. As you can see, the settling time reached here is 4.46 seconds. It is a little more than the 2 seconds we desired, but still it is a very robust response from the compensator. You may also notice that the settling time is lesser compared to the PID controller. Here is the root locus plot of the compensator. Starting off at the far right hand side of the plot, we will see here that there are two poles very close to the origin. Followed by these points are two zeros and one more pole. This means that in total there are three poles in the system and two zeros. And we know that this system is stable since it is symmetrical about the real axis. We will now look at the body plots for the compensator. For the first part, we will look at the magnitude of the body diagram. From this diagram, we can determine the corner frequency is equal to 10 to the power -2. The body plot exists for a wide range of frequencies. Furthermore, the phase part of the body diagram shows us that there are a lot of phase changes in this body diagram. To conclude, after analyzing both the PID controller and lead-lag compensator in a MATLAB simulation, we found out that the compensator had a more robust response and was a more stable system. Also, for the temperature control process, a compensator will be a more reliable system. Thank you for viewing this presentation. I would now like to take the time out to thank our lecturer Mr. Ali Mohammadi and our tutor Mr. Vinit Prasad for guiding us throughout this project. Thank you.